So I'd like to confirm the answer in two ways, and we need to think somehow deeply in these cases, especially how to use lemma 1 and lemma 2. Lemma 2 actually is explained after this example 713 on page 243. So the reader is assigned to try another solution, somehow severe steps. We need the lemma after the explanation of which is explained after the examples. So firstly, this dot above this, on top of this above this dotted line is the solution, which is written in the textbooks, and the bottom is another solution, which is explained by me. Half is written in textbook as a hint for readers. As far as explain this and think about how to use this lemma, and 4 steps procedure and 2 extreme cases are used. How and why. The problem is common source amplifier having feedback from output to Vin as a register value is RF, and I1 is constant, with no noise, and lambda equals 0, which means M1s, NMOS M1s are out going to infinity, and neglected when considering the R out in parallel with RF and RO. And in these cases, find the expression of V sub n input squared bar and I sub n input squared bar. Input voltage current and input noise voltage, input referred noise voltage and input referred current noise power. 1 and 2. At first, we showed the input to get what? When we show the input, there's no input noise current power loop to the source. Now only the voltage noises appeared effective and can be considered. And to use lemma 1, which can give us the information about V in or I out. Example, I out is known and GM is known, then I out V in equals I out over GM, which is written there. Up here, GM is R out over V in. When I out and GM is known, V in equals I out over GM. To use this lemma, we need to short the output to current through the output. That shows the output, and gate is input. In this case, input shorted case, which means actually voltage noise, but time invariant linear circuit is used to guess and to derive the constant conductance GM, like this: output shorted, input shorted, but being input shorted, but V equal applied. And this we know I out from this also need to shorted to use I out and GM. Output and input also shorted, and when output shorted, in this case input shorted case noise equals IN sub 1 of output squared bar. Previously I mentioned, and also this textbook mentioned 1 and 2 for input shorted noise suffix and input open noise suffix respectively. So IN1 out squared bar equals, in this case, INR squared bar plus INM1 squared bar. Then we know these components noise power 4kT RF, and this is 4kT gamma GM. Both 4kT RF is voltage and current is 4kT over RF. So 4kT gamma GM plus 4kT over RF equals the output noise current I sub N1 out squared bar. When we know the output voltage noise, current noise, we use shortcut to utilizing this lemma 1 as V sub N input squared bar input refers noise power equal IN1 out squared bar divided by GM squared because of this. Well, and this equivalent circuit gives us the information about GM simply. And you can derive from this the GM, capital GM, transconductance of this amplifier, and we get V input refers noise shortcut way. So first, this textbook shows the example of solution using input output shorted model to get shortcut from I out noise, output noise to input refers noise, using finding conductance, and I out using lemma 1. And on the other hand, V sub N1 out squared when input shorted is given by IN1 out squared times R out squared. R out is given by input shorted circuit like this. V out is applied by voltage sources, and V over I equals R out, because V equals RF, voltage drop, input shorted. So R out equals just simply RF. So IN sub 1 out squared bar times R out squared is VN1 out squared bar. From this, 1 sub B, the 2 is one is get this divided by the voltage gain. In both cases, voltage gain is the absolute value of AV equals the absolute value of 1 minus GMRF, which is explained next slide. Next, I will write down the expression next. But AV equals 1 minus GMRF, or AV squared equals GMRF minus 1 squared, or 1 minus GMRF squared. Both is okay. In most cases, AV is known simply after after writing up the equivalent circuit to get voltage gain, and from this we also get V sub n in squared bar from Vn out squared bar divided by AV squared. And in this solution, we open the circuit. When open the input, no Vn in squared bar, no input referred voltage noise is appeared, and there's no concern with input noise. Just input current noise is to be considered, and we also use this equivalent circuit to I in to I out, which is I out over I in equals capital A sub I, which is current gain. To get current gain, use this simple equivalent: open input but injecting I in. We can inject I in to the open circuit and get I out. And from this, we know AI is what? Knowing AI, A sub I, we know I sub in, which is noise in. So power is equals I sub in squared, noise equal I out in I n 2 out squared bar, which is open. In this case, we need open circuit noise current, and which is I out is fitted to the I sub n2 out squared bar, and so I n2 out squared bar divided by AI squared equals I in I n in squared bar input referred current noise. That is the solution written in this textbook on page 243. And another solution we recommend is to open circuit output noise, use output noise of open circuit, and use lemma. Actually, we need lemma Vn squared bar equal In squared bar divided by Gm squared. This lemma. When open circuit, there's no input noise sources appeared. Just current is injected like this. This current is injectable when open, but we need to know output voltage noise. But in these cases, the same. We know Vn of R, Vn squared bar of register, and the channel noise, current noise In2 or when open input is open or channel, just two. Thus, how we need to know the input voltage, input referred voltage, as is appeared even though input is open, but this is must be proved. But we utilize this lemma always because of the proof after this textbook, page 243 and 44. This channel noise equal I and M2 squared bar equal 4kT gamma GM divided by GM squared is input reference noise. And these two voltages non-correlated is simply series connected and add up all getting to all lead to the output noise opens when open input opened of with N2 out scale bar. So Vn2 out scale bar equal Vn squared bar times Vn in M12 squared bar equals 4kT R plus 4kT gamma over GM. Just that. So when open, Vn2 out squared bar is different from input shorted Vn1 out, In1 out squared R out, RF squared. This is different because there's a feedback RF other than compared by the previous common source stage, simple common source stage, no feedback cases, or in general, when we short the input, we just equalize the short output noise, output current only. Open and short connected together is the lead to the misunderstanding, wrong answers in general, or is this like this? So we need to take care of it. Input shorted or input open. So when input shorted, we use input shorted, output current noise, voltage noise is equivalent. Exchange each other, exchangeable each others. But short and open, between short case and open cases, we don't do that. We don't have. We must not compare the output noise or current noise exchangeable. And now that Vn2 out squared is given, what is input voltage noise? Input voltage noise is in this case given by this. This divided by AV squared is input voltage noise. And Vn out squared. This divided by voltage gain is the same or not? No. Unfortunately, this is right equal as V naught 1b equals 1, but 1b not equals Vn squared, Vn out squared bar divided by AB squared. And because we open circuit gain, open circuit output, open circuit gain. Oh. That have to be, it must be considered. The point is have to be considered. Okay, leaving this difference, we need to get input deferred noise I sub n in squared bar, and this is open. We can apply open circuit current noise, and current noise to Vx, node Vx, voltage Vx, node X, which is Vx, and input impedance is given R in, like R in, the Vx equal R in In, so Vx squared bar equal R in squared in squared bar. This is amplified by AV squared to get Vn out 1 squared bar when output is open. Output is open, out Vn 2. Vn 2, this is Vn, not V. This is 2. When output open, there's no voltage noise, current noise only, and appearing V out 2 out, Vn out, and 2 out squared is the same. So this Vn 2 out squared is the same topology from the conditions given is compared equivalently. So the one just derived is the same as AV squared bar times R in squared. So I in squared is V and 2 out squared divided by AV squared divided by R in squared. R in squared. R in is given this. When output open and input open, we can apply V in. When we apply, what is R in? There's no current to gate because there's no capacitance. We can neglect small parasitic capacitance and another gate resistor. So just I in is there. So even RF is existed, there's no difference to of R in, no difference compared to just simple gate drain connected, diodes connected N channel input impedance R in, which is 1 over Gm. Then 1 over Gm and 1 minus GMR all over squared is known, and this is known. So In in squared bar equal known. This RN in squared is the same as we just derived the textbook, like from current, using current gain. You can compare the solution yourself, see, very easily. The problem is what is R in this case, and what is Vn 2 out squared when In in squared bar is applied, and what is voltage gain, DC voltage gain. So these equations are also applicable. All of these equations are applicable only for low noise, low frequency. So we consider some low pass filter is applied to this system, and we don't mention higher frequency components of the noise. And then I've just left the problem, the difference of, which is the difference of this VN squared and this VN squared, just divided by VAV. This is a problem left behind to me. Or what the heck? V out. This is V1 out. In this case, we use AV, and now we get the same result of V n in squared using this, and using this divided by AV squared equals the same, but using this divided by AV squared is not the same, because open circuit output noise not equals short circuit output noise, just because that. Now, which is correct? The problem is this divided by AV squared or this divided by AV squared, which is a real input referred noise. Input referred noise. But when open circuit, there's no input referred noise. Just because that, I think, when utilize open circuit model, we don't derive the input referred voltage from output voltage, just total output voltage divided by AV is not the open circuit input voltage noise, because we don't have input voltage noise appeared when input opened. So we don't use this. In other words, on the other hand, we have input referred noise when input shorted. The total output noise derived from input noise shorted is applicable to get input referred noise divided by voltage gain squared. That's the point. Okay, so this is right. This is correct. And this divided with not the input referred noise, because this model, from this model, you can only know the output noise, and input noise can't be known. The output noise, this output noise just so we can say that Vn1 out squared and Vn2 out squared is different generally, because it is extreme cases in two ways. In two ways, extreme cases, we can use these values to derive input referred current noise and input referred voltage noise in some way, in different using different lemma 1 and different lemma 2. When we show the input output and using transconductance lemma 1, we can derive Vn1 out or In1 out squared. Using these, we can get Vn input referred noise, and using lemma 2, we open circuit and open circuit output voltage noise using lemma 2, because the equivalence input noise is virtually can be applied by In squared over Gm squared of most devices. But these two voltages, extreme cases, just used to get input referred current noise and voltage noise in different ways. This is using current gain. This is using this is using voltage gain, just voltage gain, and this is using not current gain. This is using just Rin times VA, Rin times IN. Both uses AB, voltage gain, which is I'll write down and in the next explanation. Maybe very simple. We've been confirming the solutions in two different ways, two extreme cases, using two extreme cases, and how and why and what the difference and what is the same. Both, when correctly manipulated, both gives us the information of input reference noise voltage, input reference noise current, the same, both the same values through different model, two extreme cases. We can use both of them, but this text recommend the shortcut ways. We want to find the shortcut way when topology is given, which is the shortcut ways. When input shorted, output shorted, using lemma 1 cases, or input open and using lemma 2, virtual input noise, referred noise, using and input impedance, using finding input impedance, getting input referred noise. Both is the shortcut. Is depends on everybody. It depends on the sense of yourself, maybe, or which is your favorable method, which is your favorable, lemma 1 or lemma 2, using finding R out or finding R in, or which is different. It seems to be difficult to get R in or RF, R out, or to utilize lemma 2 or lemma 1, which is difficult. Totally considered, we select two extreme case method: input shorted way or input opened way. In the meantime, intermediate value of output noise is different because already said, because of the reason already said, different too, but different approach, intermediate different value to the same input referred voltage and current noise. It's very interesting. We can use two ways, which is easy to applicable. We can select either way. That is more easier. That is easier way. Either way, more easier. We can select either way more easier. to the problem given. To get input referred voltage noise or input referred current noise. But background, all of these background, there's 4-step procedures. Finding noise sources, and finding noise sources power spectrum in each component, finding the transfer function or voltage gain of this of the topology considered, and connect the carrying non-correlated correlated cases, connect sum up the voltage noise and current noise separately, and derive the equation spectrum times transfer function equals spectrum output. So using these 4 steps is underground basic method, basic principle to deal with amplifier or device noises. So with the underground of the 4-step procedure, and selecting the 2 extreme cases for which is easier to be applied to the problem in concern. That's all. And next, I can derive the voltage gain of this feedbacked common source amplifier.